Okay. Don't forget that the Learn Smart for Chapter 8, I think, should be done Monday evening. I think that's what I set it for. We should be through the chapter by Monday, I think, the way it's going right now. But we'll see. If the chapter goes longer, do you need me to extend that Learn Smart? Yes, no? Actually, I'm curious because I haven't asked you a lot about the Learn Smart. Do you find it helps you prepare before you read the lecture or read the book or come to class? Or is it better to go to Learn Smart after you've seen it in class? After? Because I hear different things from the book publishers. They were here yesterday talking about Learn Smart. And they gave us this trial version this year, so that was very nice. So it seems overwhelmingly after. Okay, so if we don't finish on Monday, I will extend that Learn Smart longer. So if you don't get it all done by Monday afternoon and their class hasn't finished this chapter, don't worry. Homework problems I had set for Tuesday. Again, if the class takes, if the chapter 8 takes longer than that, I will extend it. There's something else I wanted to ask about Learn Smart. Oh, there's some social features in Learn Smart, right? Like competition and points and competing against each other. Does anybody use that? Does it help you, inspire you to do more Learn Smart? Who's competing with each other? Okay, we have 2 people competing. Okay. Yeah, I was trying to tell McGraw-Hill, I don't think my students are using that. And they're trying to sell, well, this is the greatest thing because they're all on Facebook and they're all Twittering, so they can compare and compete with points and try to beat each other in Learn Smart. But I don't think so. If you do like that feature, let me know because I'll certainly pass that on to the publisher.
Just kidding. Sorry.
Okay. Of course, nothing can compete with nucleophilic substitution, right? So on Wednesday, we talked about the substitution reaction mechanisms, and this is a little different than the substitutions we talked about in the alcohols chapter, where we were doing things mostly under acidic conditions with alcohols. In this case, we're talking about substitution reactions that are, this is probably the best way to do nucleophilic substitution, when we have a carbon bonded to a very good leaving group. So that bond is weak enough that carbon is electrophilic. So there's a partial positive charge on the carbon, and we have a good nucleophile, such as in this example, the hydroxide ion. And that undergoes a substitution reaction. Essentially, you think about that hydroxide as, I don't know, the electrons are like an iron fist coming from behind and kicking off that leaving group. It's almost like that because it happens in one step when we deal with the mechanism where we have SN2 substitution. Okay, and there are a lot of details and aspects that would allow us to do this reaction in this particular pathway versus an SN1 pathway. There's also stereochemistry consequences to this reaction. Okay, because bond forming and bond breaking occurs in a certain orientation. The bond that's breaking in this case is the carbon-imine bond, and the bond that's forming is the carbon-oxygen bond, and they have to be 180 degrees opposite. So in the process of these bonds changing and the electrons moving, the other groups on the carbon have to move also. Because we start from an sp3 hybridized carbon, but we're switching 2 groups and inverting that carbon like an umbrella. So if there was stereochemistry at that carbon, in methane, of course, there's no stereochemistry, but if there were 4 different groups attached, the configuration would invert. Okay? So we talked about some of the aspects of this reaction, the leaving group ability. So the ability of the leaving group or the weakness of that bond has an impact on the rate of that reaction. So it works best with things like iodides and bromides. As you look at the right side of that chart, NH2 minus, OH minus, F minus, those are terrible leaving groups. You're not going to break them under normal SN2 substitution reactions like this. So leaving groups are one aspect. The rate for the SN2 substitution also depends on how accessible the carbon is to the nucleophile. Okay, so if you have a nucleophile coming in, it has to approach the carbon that's the electrophilic carbon, the one attached to the leaving group. So if there are no other groups on there, of course it's wide open. You can easily form the bond from behind that carbon-halogen bond. Okay, but as you start to substitute and put more groups on there, it gets more and more crowded. That makes it more difficult to do this direct substitution reaction. So if you get to a situation where you have 3 groups attached, a tertiary halide, that's essentially never going to do an SN2 substitution reaction with the kinds of nucleophiles we're talking about here. It won't happen. Substitution would have to occur by a different mechanism. By the way, I've just shown an example here with hydrogens and then adding on methyl groups. But if you actually have substituents on here, even if you have, say, this secondary substituent, or even this primary bromide, it's a primary carbon, and this is something much bigger than a methyl group, that also can block it. So compared to this primary bromide, if you had a large T-butyl group here, that would also be a really slow reaction compared to that one. So it doesn't really matter. You have to think about overall the crowding around the carbon where you're forming the bond. But in general, in terms of degree of substitution on the leaving group carbon, it follows that trend. Okay? The types of nucleophiles matter. We were starting to talk about this near the end of the class last time, how nucleophiles, the nature of a nucleophile, there are different aspects to that. So if you look at a neutral species, which has a lone pair, remember all of these reactions of a nucleophile, they really are all Lewis-based reactions. You have a lone pair that's forming a bond, or giving those electrons to form a bond. So water can be a nucleophile. It's got a lone pair, and that could form a bond to an electrophile, to a carbon. But it's not a very good one in this kind of reaction. Okay, if you deprotonate that and make a hydroxide, it's a much stronger nucleophile. Okay? It's also a stronger base. It can deprotonate things quite readily as well. So as you go from neutral to charged, if you're comparing the same kind of atom like OH, OH, go from neutral to charged, weaker, stronger. If you go to the right on the periodic table, it becomes a little bit stronger or weaker. So you go from nitrogen, you go to the right, it gets a little bit weaker. So as the atom gets more electronegative, comparing oxygen to nitrogen, oxygen is more electronegative than nitrogen. The nitrogen is a better nucleophile than the oxygen, okay? Comparing two neutral species, or if they were both charged, comparing both charged. As you go down the periodic table, especially with the halides, we illustrate it as a leaving group. Iodide is a better leaving group than chloride, but it's also a better nucleophile. And I actually misspoke yesterday talking about the direction of exchanging halogens. You actually exchange for the better nucleophile. So you can take a bromide and make an iodide. Sorry about that. I tried to put a little note on the video yesterday that I made that mistake. In any case, there's obviously two different things going on here, right? The charge, but also the ability of the atom to donate those electrons. That is how loosely they're held. Okay, and that's something called polarizability. If it's more electronegative, it holds the electrons tighter. If it's less electronegative, it holds the electrons looser. That, in part, explains the difference between water and ammonia. Ammonia, the nitrogen is holding electrons a little bit more loosely because it's less electronegative. That would explain the difference between iodide and chloride. Okay? Iodide is a better nucleophile than chloride because it's holding onto those electrons more loosely. It's less electronegative. And also, the electrons are further away from the nucleus. So the bigger the atom, the easier the electrons are to form a bond because they're not held as tightly by the nucleus. Thiol or thiolate versus hydroxide. The sulfur, you go down the row on the periodic table, the sulfur is a better nucleophile because of just that reason. Now, if you're comparing the same atom, the base strength is important. So water is a very, very weak base. Hydroxide is a much stronger base. The stronger that base, the better the nucleophile. But then you compare hydroxide to the sulfide. Sulfide is a weaker base than hydroxide. But it's a better nucleophile. It's because of that polarizability. Okay, so I want to stress that because it really is important when we talk about all of these substitution reactions. Okay, we also talked about the SN1 mechanism. This is a mechanism which occurs in the case that you can form a stable carbocation. Right? So in the case of SN2, it's about having the less crowded environment so you can get the nucleophile close because you need the nucleophile to interact to kick off the leaving group. Okay, both of those are involved in the rate determining step since it's one step. Nucleophile and alkyl halide. In this case, the reaction doesn't depend on the nucleophile, and that's the key difference. Here, what's important is the ability to form a carbocation, and that's all about the structure. Okay, a tertiary carbon is going to easily form a carbocation and not do an SN2 reaction because it's too crowded. The only way it can do substitution is if the bond breaks first to form the intermediate, and then the nucleophile, in this case, a neutral nucleophile like water, will add pretty readily. Okay. What characterizes SN1 reactions is the nature of the substrate, most importantly, and the fact that we don't have any strong nucleophiles or strong bases. Okay, we have a neutral nucleophile. Most often it's the solvent. So in this case, if it's water, or water with some methanol or ethanol. It could be an alcohol solvent also as the nucleophile, often referred to as a solvolysis reaction. So notice the difference between SN1 and SN2 in terms of the types of requirements. I'm glad that coming up. Okay, I come up in a minute. Because the SN1 reaction, let me just back up for a second. Because the SN1 reaction goes through a carbocation intermediate, if you happen to have stereochemistry on that carbon, what would happen to the stereochemistry in the product? Well, since this carbocation is a planar intermediate, right, and then the nucleophile, in this case water, could add from this side or could add from that side, you could form either product, either an enantiomer product. If those R groups are different, right, that would be a stereocenter. You can form either an enantiomeric product. So unlike SN2 reaction, where the bond breaking occurs at the same time the bond is forming to the back, and it's inverting completely, this you would get if you had a chiral alkyl halide. You'd end up with a mixture of enantiomers in the product. Okay? Sometimes that's a 50-50 mixture. Sometimes it's not necessarily a 50-50 mixture. But it's not a pure inversion either. So this is actually an interesting example on the next slide. Substitution reaction of a chiral bromide. Okay, we have, what do we have? The R configuration at that carbon that the bromine's attached to. And if you heat this up in water and some ethanol helps dissolve the organic molecule because it's organic. But there's water present, and water is the nucleophile that's reacting here. So we end up with a hydroxide group. Okay. Notice, interestingly, we get two different enantiomers. We get the S configuration. That comes from inversion of the original stereochemistry, right? Inversion. And we have the R stereochemistry. That's what we would refer to as, from the starting material to the product, that's retention of configuration. So we have the same, but we get a mixture. And it's because what's happening is you take this and you form a carbocation. And we know the structure of the carbocation is planar, and you can then add the water to either face or either side of that. Okay, just like I showed in the previous slide. But interestingly, in this reaction, they don't get a 50-50 mixture. Sometimes you don't. A 50-50 mixture would be a racemic mixture, right? They get an 83 to 17 ratio. Is that something you could explain? Why would you favor one over the other? Remember when we talked about stereochemistry of reactions in the stereochemistry chapter, that the only way you could have something chiral being produced in the product is to have some chirality to begin with. And if this carbocation were completely separated and alone, that should give us a 50-50 mixture of water adding. There's nothing chiral in this intermediate. Okay? But in fact, things aren't quite that cut and dry or black and white. What happens in a reaction pathway is maybe when the bromide comes off, that bromide ion doesn't separate away completely. Okay? Your book actually has a really nice figure for this, to explain this. Come here. So if you take a look at this, this is an example of how you might see something other than a 50-50 mixture. So here we have a carbon-halogen bond, which is breaking. Okay, it forms a carbocation, but that anion that came off, it's sitting right here. Okay, so even though you formed a carbocation, if the nucleophile adds or reacts before you can separate those ions apart, that nucleophile can only add from this side because this side's blocked, right? Just because the ion hasn't moved away. But it depends on how fast that next step happens. It's still a two-step reaction, but if this happens really fast before you actually physically separate the ions, you can actually see some amount of addition on that side. If that separates apart completely, and this is lived long enough so the nucleophile could access it from both sides, you would get a 50-50 mixture. Okay, so in fact, when we actually observe SN1 reactions, sometimes, starting from the chiral molecule, we don't see complete racemization or complete 50-50. Sometimes we get some selectivity in that process. But what we always see is a mixture, though, not a complete, clean inversion reaction. All right? Any questions about that, those details of that stereochemistry?
So, depending on speed, it's how fast that leaving group is kicking off there.
Right, and there are many complicated factors. How fast that leaving group of that ion actually separates away. This is what we would call an ion pair, or a contact or a close ion pair. Actually, if you think about it, all these things are not being done in a vacuum. There's solvent around. The nature of the solvent actually depends how much it can stabilize ions, dictates how fast that might move apart, and then the nature of the nucleophile, if the solvent is a nucleophile, how much there is, or what concentration of the nucleophile is present. All those things can influence that. So the fact that in that example, we get an 83-to-17 mixture, if you change some aspects of the reaction, that would probably change that ratio, depending on where you are along this reaction path when the nucleophile adds. But I think to make it simple, just remember that SN1 reactions, carbocations, you'll get mixture of enantiums. Often that's a 50-50 mixture. Sometimes it's not, but it's still a mixture. And the other aspect of doing an SN1 type of reaction is that we're forming carbocations, right? So in a carbocation intermediate, it could undergo rearrangement if it forms a more stable intermediate. So here, for example, if we have this bromide, secondary bromide, and it forms a secondary carbocation by ionization. Okay. Then we could add water to that carbocation, but we could also do a carbocation rearrangement, just like we talked about before. So that hydrogen moves over, we put the carbocation on the tertiary carbon now, and we get the product of water added there. Okay, so just be aware that whenever you have formation of carbocations, whether it's a leaving group breaking like this, or whether it's protonation of an alcohol and forming a carbocation, or protonation of an alkene and forming a carbocation, it's possible those could undergo rearrangement. Okay, this sort of summarizes some of the features and compares these two different mechanisms for substitution. Remember, SN1 is a two-step process where we form carbocations, and SN1 is a one-step reaction where the nucleophile is coming in and forming the bond at the same time that the leaving group is leaving. So if we look at all these different features of the reaction, one of the important aspects of this is the nature of the substrate. Okay? The nature of the substrate, or the electrophile, in terms of the substitution of it. So for an SN1 reaction, we need most stable carbocations, so it works, essentially will only work with tertiary substrates. Sometimes secondary, but not very much, but tertiary definitely. For an SN2 reaction, it's not going to work with a tertiary substrate. It has to be primary or secondary. Okay? So that's a clear difference. They are opposite in terms of their preference for what kind of substitution of the substrate the reaction will work under. The nucleophile, that's also something important to say which way a reaction will go, one way or the other. So in this more gray area, when we're talking about, say, a secondary system, if you have a strong nucleophile, which is required for an SN2 reaction, it'll do SN2. If your nucleophile is very, very weak, it might not do SN2 if you can stabilize a carbocation on a secondary carbon. A weak nucleophile would work. Okay? So remember, in the reaction to form carbocation, the rate determining step, or the hardest step to do, is breaking the bond to form that intermediate. That doesn't involve the nucleophile in the next step at all. That's a faster process than the first one anyway. So the nature of that nucleophile doesn't have a whole lot of influence on the SN1. If it's strong, it could go for SN2. In all cases, having a good leaving group helps. So the leaving group ability really is the same for both of those reactions. And there are consequences if that carbon with the leaving group on it is a stereocenter, right? So in the SN1, we have racemic or mixtures of enantiomers. And if it's SN2, it goes with complete inversion of the stereochemistry. Okay, so that really ties together all of the different properties and features we've been talking about with regards to these two mechanisms. The one important thing that I haven't talked about yet is the nature of the solvent. And the solvent is critically important. And it can dictate which of those pathways the reaction undergoes, depending on the solvent. The solvent can influence all aspects of these reaction mechanisms. So if we take a look at this, okay? Our generic, yeah, question?
What are the characteristics of the good leaving group?
The characteristics of a good leaving group? It's got a weak bond and a more stable anion after it comes off. So whether it goes by SN1 or SN2, there are some common features that require certain aspects or certain properties of a solvent. That is, you need solvents which are polar. Okay? If you think about either mechanism, you have a carbon attached to a halogen. That bond has to break. Okay? And during the breaking of that bond is becoming polarized in the transition state. So you're actually separating charge. As this bond comes off or gets longer into breaking, there's more negative charge on the halogen and more positive charge on the carbon. So if you can stabilize that, it'll lower the energy of the transition state. Okay? We also have, usually, ionized species present in terms of the nucleophile. So sodium hydroxide. We have a nucleophile which is an ion. So in order to solubilize ions, you have to have polar solvents. So these are polar reactions. We have to have polar solvents. Okay, but there are two kinds of polar solvents that have different aspects to this. Here are some examples of some various solvents. So all the way from nonpolar solvents like hydrocarbons, hexane, benzene, carbon tetrachloride, completely nonpolar. They have no functional groups which polarize at no dipole moment for those species. So those solvents, if you're to dissolve your reactants in there, you're not going to dissolve sodium hydroxide and hexane. It'll be insoluble. So unless you can get reacting species together, if they're in different phases, solid and liquid, it's hard to get them together. Not impossible, but hard. But it would retard the reaction. Here are some examples of polar solvents. They have some functional group which makes for a polar molecule. So the molecules have a dipole. There's a property we call dielectric constant, which is a measure of polarity to some extent. And I've separated these into two kinds of polar solvents. Okay, what we call polar protic solvents and polar aprotic solvents. What that means is there's a hydrogen attached to something other than carbon, usually an oxygen or a nitrogen. These are examples of protic solvents with a hydrogen attached to an oxygen. Just like water, it has somewhat of an acidic hydrogen on it, right? A proton, if you will. Protic solvents. And why would we think that would interact differently with our species than aprotic solvents? Here are some common solvents which is used in substitution chemistry. Acetonitrile, CH3, C triple bond N. That triple bond nitrogen is polarized because nitrogen is a different electronegativity than carbon. So there's a dipole moment in that molecule. DMSO, or dimethyl sulfoxide, also has a polarity in this direction. Oxygen is more electronegative than sulfur, so it's polarized in that direction. Same thing with this dimethyl formamide. It's polarized towards the oxygen, and this phosphorus compound HMPA, polarized towards the oxygen. So all these are polar molecules, but what they don't have is a proton or a hydrogen attached to an oxygen or nitrogen. Yes?
We just did HPLC up in the lab
Mm-hmm.
this week.
Good.
We were using nitrile as
Yes.
a solvent.
Mm-hmm.
So when we put something like a polar substance like caffeine in the acetonitrile, it's the acetonitrile that's causing the...
The acetonitrile is polar, right? And if you're using this in your HPLC experiment and you need to dissolve a polar molecule into it, you need a polar solvent to dissolve a polar molecule.
Okay. So
Right.
it causes...
Absolutely. So all of these are polar molecules. The difference with the protic solvents is the ability to hydrogen bond. Okay, like water forms networks and alcohol forms networks. We talked about this when we talked about the alcoholics chapter, right? You have water, and then you have some other, water, for example, and you have hydrogen bonding to that, so you form networks. That can cause some problems in some reactions. So in general, SN2 reactions suffer with protic solvents. But you still need polarity. So aprotic solvents work great for SN2. And it's the opposite then for SN1. So let me show you some details of this. Here are some of this is a chart from your book as well, showing the dielectric constant. That's a measure of the ability of a solvent to stabilize charge separation. So the greater the dielectric constant, water has a very high dielectric constant, we consider that the more polar solvent and the greater ability to stabilize polar molecules or polar transition states. By the way, the measurement, if it's completely in a vacuum, the dielectric constant is considered 1. So the greater the dielectric constant, the more polar, the more able to solubilize and stabilize those kinds of charges. So let's take a look at this. Here's this substitution reaction we've been talking about, an SN2 reaction mechanism, where the rate of the reaction, the highest energy transition state, is the one, well, it's just one step. So it involves both the nucleophile trying to form a bond, you need that strong nucleophile, and the bond to the halogen breaking. Okay, these are all polar molecules with various polarities. But if you take a look at this, there's a clear difference. Water has one of the highest dielectric constants. It's one of the more polar molecules as a solvent. But if you compare methanol, water, those are both protic solvents. Compare the reaction rate for those versus DMSO, DMF, acetonitrile, HMPA, these other non-protic polar solvents. These go much, much faster. Okay? And then you should say, well, why? If they're all polar, what's wrong with the protic solvents? Well, first of all, we should mention what the important thing about the polarity of the solvent is. So, for example, here's the structure for dimethyl sulfoxide. As I said, it's partially, it's polarized towards the oxygen, so it's a polar molecule. And if you think about all these species in the reaction, what is the DMSO doing and aiding in this reaction? Well, one of the important things, of course, is solubilizing our nucleophile. Like I put hydroxide, but it's sodium hydroxide or potassium hydroxide. You need the negative ends of the polar molecule to help, it surrounds the cation, it helps stabilize it, and separate it from the negative ion, which is our nucleophile of interest in this particular reaction. That nucleophile, the solvent that surrounds it, will surround it, pointing its more positively charged end towards it. Okay, that stabilizes it. But then allows them to separate and actually be solubilized, go into solution. And that helps a lot. The same thing is true when you think about the CI bond in this example. As that bond lengthens and breaks, you're polarizing it, so iodine has more negative charge. And in the product, iodide comes off. You need to have polar molecules, solvent molecules, to stabilize that negative ion that comes off as well. So polar molecules help this reaction. But for this SN2 one-step reaction, we still need the nucleophile to be available to form a bond. So we don't want to stabilize it too much. Okay, and that's what happens with a protic solvent. So if you have something like water, the water forms a tighter interaction with the negative charge because of the protons on the oxygen. So that's why protic solvents actually retard the rate of SN2, because it's taking the nucleophile out of the picture. It's making it less reactive. Does that make sense? Yes? Okay, we're still with you. So for this reaction, we need both partners to be stabilized but still available to form the bond. So you can't stabilize the negative charge too much. That's why even though water is polar, things will dissolve. The nucleophile is weakened, and that makes the reaction less effective. Okay? On the other hand, in a SN1 reaction, polar protic solvents work the best because we don't need a strong nucleophile. It's formation of the carbocation, which is most important. And that is stabilizing the plus charge on this carbon by polar solvents' negative ends, and bringing that iodine very, very stable. And that helps with the hydrogen bonding. So water in this case, oh, I used bromide, sorry, same thing. Carbocation is stabilized by the negative ends of water. The bromide that comes off, or the iodide that comes off, is made really stable by those hydrogen bonds. Okay? So protic solvents work just fine when we have SN1 mechanisms and we don't need a strong nucleophile because that second step is much faster than the first anyway. The delta positive hydrogens are helping to stabilize that. And then we don't have to worry because our nucleophile is water anyway, or whatever the solvent is. Okay? So that's the nature of the solvents. Let's see. I'll come back to this next time. I want to stop now and take a quiz today. So on Monday, we'll summarize all this again and continue some of the other aspects of the substitution chemistry. You knew it was going to happen, right? It's been way too long.